Let's solve these equations. Cosine x equals -1/2. X is going to be in degrees. When we're looking at this, what did I say that we're always going to do? Draw our unit circle. Now we have cosine. Now for some this can be a little bit confusing because our angle here is x. But we can think of this in terms of x and y on the circle. This is graphing the line x equals -1/2. And we're going to have to be able to deal with that idea that instead of saying cosine theta, it's just cosine of some angle here. X equals -1/2 is a vertical line at -1/2. And we see we have two solutions. And you know what those solutions are since you're experts on the unit circle. It is 120 degrees, our top one, and our bottom one is 240 degrees. Now, given that there's no restriction on x, we can't just say these two answers. They're an infinite number. We have to add all of them, plus 360 degrees n, plus 360 degrees n, and n is an integer. Now let's take a look at the next one. We have sine x equals -√2/2. Remember, that's about -0.7. So we look at our unit circle. Sine is y. Y equals -0.7. That's going to put us somewhere around here. And we see we have two solutions there. And we're in radians now. And this will be 5 pi over 4 and 7 pi over 4. Again, there's no restriction here, so we have to add up every coterminal angle with it, plus 2 pi n, where n's an integer. Now what I'd like to look at right now is our calculator. So what would our calculator give us? Put it here, see if I can get that to show up. First thing I want to do is, in problem number 1, let's hit mode and make sure that we're in degree mode. Right now you're probably in radian mode, so just move it over, and you would just, if it was there, you'd move it over to degree and hit enter. And then let's go back and we'll say, how can we solve this equation using our calculator? Well, what we'd do is we'd come down here and we'd say x equals the inverse cosine of -1/2. So we'd say second cosine and then type in -1/2 or -0.5, it doesn't matter, and hit enter, and it gives us 120. It only gives us 120, and the question is why? Let's take a look at the second one. We would say x equals the inverse sine of -√2/2. So on there we'll say second sine, and then we say negative square root of 2, close that, divide by 2, and it gives us, that didn't give us either of these. Oh, I'm still in rate or degree mode, and I want to be because recognizing the decimal equivalent of pi over 4 is not so easy. But this is the equivalent of saying negative pi over 4. Now, compare that with the answers we have, 5 pi over 4, 7 pi over 4. Which one is the equivalent of negative pi over 4? Well, 7 pi over 4 is coterminal with it. Now, why is this doing it? The calculator is only given one answer. What the calculator is doing, and what the notation our book is going to use, the calculator gives only x equals capital inverse cosine of -1/2. And this is saying the function inverse cosine. The way you would say it is inverse cosine. You can also say arc cosine. I'll use both, and both are good. And the same thing over here, our calculator is going to give capital inverse sine. And when the book uses the capital, what it's saying is that there's only one answer to it because it's a function. Inverse sine or arc sine. And the function can only give us one answer. Now, take a look. What were both? We have to then realize, before I go on, we have to realize what we are solving. We are solving for this problem. Even though the calculator gives us one answer, we realize there are two because we can see it in our unit circle, and then we have all the coterminal ones. Similarly, on the sine one, we see there are two answers, and so we have to use, if we're using our calculator, we have to use that as a starting point to get the rest. Now, what is an arc trig function? When we used it over here in problem number 1, we got 120 degrees, and when we used it in problem number 2, we got negative 45, and we realized since we're in radians, that's the same thing as negative pi over 4. So when I say, what is an inverse trig function? When you find the arc sine, arc cosine, arc tangent, etc., what is the answer? How can you describe those answers? They are an angle. So you want to realize what it is you're finding. If you have that, you'll be much better prepared to do what we're going to do. All right, let's start to look at these inverse trig functions. So first of all, does y equals sine x have an inverse? Write that question down. Does y equals sine x have an inverse? If I sketch the graph, we know the graph looks like this. Let's go on both sides. So we have 2 pi there and negative 2 pi. Does that graph have an inverse? What does it mean to have an inverse? How can you tell if a function has an inverse? Remember, it has to be a one-to-one function. It has to pass the horizontal line test because the inverse switches the x and y, and if the function doesn't pass a horizontal, the inverse won't pass the vertical. So is this function one-to-one? No, it is clearly not. We can draw our line across, and we can see that it crosses in multiple places. In fact, it crosses at an infinite number of places because the graph keeps on going. So when you wrote that question, does the sine have an inverse? The answer is no. But how is this possible? Because we just used inverse sine this function in problem number 2. And we wrote it right up here. We have inverse sine, we have inverse cosine. What are we going to need to do? What did we do back when we were studying this? What we had to do is limit the domain. What can we limit the domain to in order to make this have an inverse? Now, one of the things you want to remember when you're limiting the domain is we're always going to include the first quadrant. And we want to, well, that's the key thing there. We want to be able to include all of our values. We want it connected, if possible, and we want it to include that first quadrant. So if I go first and second here, will this have an inverse? No, it still doesn't pass a horizontal line test. But I know I'm going to include my first quadrant. So if I can't continue forward, because it starts going down, I'm going to have to go backwards. And I keep on going until it stops or it comes back up. So that's going to be at this point. So I'm going to go from negative pi over 2 to pi over 2. So now, if y equals sine x is restricted to negative pi over 2 to pi over 2, and what would our y values be? And our y values would be negative 1 to 1. Then y equals inverse sine of x is a function. And what is its domain? Its domain will be Let me just put D there. I'm not using all the formal notation, but that's okay. Remember, the x and y are switched, so we're going to say between -1 and 1, and our range now will be between -pi/2 and pi/2. Let's sketch this graph. One way to do it, well, we're going to say here, and our domain values are going to be from -1 to 1, and our range values are going -pi/2 to pi/2. One way to do it is to take our paper. Now, we're going to have to realize our orientation is switched a little bit. So we have a positive here, starting at 0, 0, the origin. When we go to pi/2, it's going to go, the y values of sine go to 1. And so it's like this. And then when we go to -pi/2, it's going to -1. Now, theoretically, we could continue this around, but would that be the function? No, that would just be the relation. And so with the restricted values, this is our inverse sine graph. Now, my scale is not perfect, but there's your basic shape of it. Let's repeat this and do the same thing with cosine. Now let's start with y equals cosine x. Cosine x looks like and then what do we have here? Does it pass the horizontal line test? No, it doesn't have an inverse, so we're going to have to restrict the domain, and we're going to include the first quadrant here. But if we go to the fourth quadrant like we did on the previous one, that doesn't pass the horizontal line test. So we're going to have to stop it this time at 0. And at what point does it start repeating when we're moving over? It's right here when it starts going back up. What is that value when cosine gets to -1? That's pi. So for y equals cosine of x, if we restrict it to 0, our domain would be 0 to pi. Then our range is still going to be from -1 to 1. The inverse, I'll just throw it over here, y equals inverse cosine. Again, we're going to use a capital. That's just what our book does, so we'll just use it. Our domain would be from -1 to 1. And our range would be from 0 to pi. And when we look at the sketch of this graph, start out in a similar way. We'll have -1 to 1, except this time what we're going to do is go to pi. And we can sketch this using that same idea I used on the previous one. So we start off at 0, 0. No, we start at 0, 1. Sorry, cosine of 0 is 1. And then it goes to, at pi/2, it goes to 0. And then at pi, it's going to -1. And so this graph is looking like that. So there's our inverse cosine. If we, let's take a look over here, and I'm going to throw down tangent. Y equals tangent x. I didn't set one up, so that's why we're just going to throw it in here. Remember, tangent is looking like this. It's that repeating over and over and over. So given our idea we're going to have the first quadrant, we're going to take this whole piece right there. We want it connected. So as far as dealing with the basic functions, that's pretty straightforward there. So if we limit this to, actually we don't have equals to, so it's similar to the sine, except since we have those asymptotes, we won't have that, and our range will be all real numbers. So what will our inverse look like? We're only going to restrict it to this first part. The inverse tan of x is going to be looking like here we'll go pi over 2, negative pi over 2. Let's see if I can do it without rotating my paper on this one. It's going to go to pi over 2, and it's in the first quadrant. So I'm going to start here, and it's going to get closer immediately to that. This time it's going to have a horizontal asymptote. So it's going to be looking like this. And then over here it's going to be coming in like there. All right, and that's basically, so this would have a domain of all real numbers. Remember, those two ways to write are the same. And our range would be from negative pi over 2 to pi over 2. So we need to know these restrictions. You need to know them and know them well. Now let's take a look at the next one. We're going to apply it to these problems here. And let's see how we're going to do this. So we're going to evaluate this inverse sine of negative 1/2. We're going to set it equal to x. And then this means solve sine x equals negative 1/2 for x restricted to negative pi over 2 to pi over 2. Why are we doing this? Because this is the function, and so these values have to be in between what we get from it, between negative pi over 2 and pi over 2. So now we can look and say, all right, where does sine equal negative 1/2? Well, on our unit circle, it's coming over here. So there's two values. Well, this one's definitely not in there because we're going negative pi over 2 to pi over 2. So this side doesn't exist. So it's just this one angle. What is that angle? You might say 11 pi over 6, and that is correct, but it won't solve this problem because it's not in between negative pi over 2 and pi over 2. So what we have to do is do the negative coterminal of that. So x is negative pi over 6. Let's do it again on this one. This means cosine of x equals negative root 3 over 2. Now what's our restriction for x? It is 0 to pi. So if we're looking at this, we're going 0 to pi. We only want the top half. We don't want this bottom half at all. Negative would be over here. And what would that value be? That'd be 5 pi over 6. Inverse tan of root 3. So we'd set that equal to x. And this gives us tangent of x equals root 3. Now what's our restriction for tangent? I'll put it using our interval notation on this one. Remember, that means negative pi over 2 to pi over 2, not inclusive. So when we're looking at that, we're eliminating this piece. Tangent's positive in the first quadrant, so that's up here. Square root of 3 over square root of 3. And that would mean that the sine would be root 3 over 2 and the cosine would be 1/2. So that would be at pi over 3. All right, note that, and I've said this, but we didn't write it, the domain restrictions of sine, cosine, tangent, etc., or the range restrictions of the arc trig functions are important. All right, let's take a look at one more here. So how would I deal with this? Remember, what is this inside part? What is an inverse trig? It's giving us an angle. So let's take this and we'll say let theta equal the inverse of negative. Use our calculator at this. There's no calculator allowed. This says that cosine of theta equals negative 2/3, but we have to restrict it. Theta is in between 0 to pi inclusive. So what we're going to do now is we're going to just set up a triangle, and we're in what quadrant? this is the first or second, but cosine's negative, so we're in the second. This would be negative 2, the adjacent over hypotenuse, and we could use our Pythagorean theorem here to say the square root of 9 minus 4, so that's just the square root of 5. So now, again, if we take into account the positive or negative of the sides, this technically is our theta, but we can use that triangle. Now, what are we trying to find? We're trying to find the sine of theta, because theta is the inverse cosine. So the sine of theta equals square root of 5 over 3. Similarly, you would say let theta equal the inverse sine of root 3 over 2. So then the sine of theta equals theta in between negative pi over 2 to pi over 2. So it's either the fourth or the first quadrant. In this case, we're in the first quadrant because it's positive. So root 3, 2, this would have to be 1. It's our standard 30, 60, 90 triangle. So we want the cosine of theta, and the cosine of, or cotangent of theta, sorry, would be adjacent over opposite. So 1 over root 3, which simplifies to root 3 over 3. And that's it.